So today I'd like to talk about some work that was done with Abhishek here at ICTS and a few of our collaborators, Cedric at HSC University Moscow, Altra Kundu at the University of Luxembourg, and Raphael Shetright, who is at Nice. So through this talk, I'd hope to explain what spikes are, why they're interesting, and what are the experimental connections with this phenomena, which is what we are most excited to share about. So to begin with, I'll be talking about, this talk will focus on the dynamics of quantum systems that are coupled to measurement devices. But to give a more general framework, I'll start by explaining how it fits in the framework of the more general open quantum systems. So essentially, you have a system which is coupled to a bath, and the state of the system at any given time is given by rho t, and rho t isn't usually a pure state. It can be a mixed state because it is usually entangled with the bath. And the system in itself has an intrinsic Hamiltonian H, which governs its own dynamics. And in such a setup, you can ask a question: what is the effective time evolution equation of the system state rho t? And this is the question that underpins the field of open quantum systems and master equations. And throughout the years, it's a few decades old, there are many master equations that people have written. The most famous of which is the Lindblad equation, which, one second, I think my mic is slightly off. Is it more consistent now? Yeah. So the Lindblad equation, which is essentially valid for when the system is coupled to a bath, which is Markovian. And then it has a few other assumptions like weak system bath coupling and the secular approximation, which I won't go into right now. So along similar lines, you can ask a question of what if you have a system that's coupled to a measurement device, which spits out an output at any given time. So for the sake of simplicity, you can consider a system that's coupled to a single photon detector, which spits out an output of 0 and 1 at any given time. And in this case, the effective time evolution equation of the system state rho t is given by a stochastic master equation. And you have this slightly complicated looking expression. But what I would like you to focus on is the part that I've highlighted here, where you have a noise term given by this dn, which is sampled from this particular distribution, which is coming from the measurement outcomes, 1 and 0. And you'll immediately see that this equation is stochastic, and it has certain non-linearities, which is to be expected because you have a measurement process and that will induce certain collapses in your state. So those of you who have done quantum 101, this wouldn't come as a surprise. And generally, this particular master equation and the master equations people write in general in the literature are for manifestly Markovian measurement protocols. So the reason I brought this up is to just give a quick-fire introduction to quantum trajectories. Quantum trajectories are known as solutions of these master equations. And you can see an immediate connection between the equation I've written on the right-hand side. If you take an ensemble average of the noise terms, you will immediately get the equation, which is there on the left side of the slide. So that which is the Lindblad equation. Okay. So given this introduction to quantum trajectories, we would like to just motivate the problem in a slightly more concrete sense. You have essentially two-level systems, and we'll be focusing exclusively on two-level systems in this work, which is coupled to, say, some kind of a measurement device, say a single photon detector. So you will have the effective dynamics given by these jump stochastic master equations, where we call the dn is equal to 1 outcome of the measurement device as the quantum jump. And you have these parameters, gamma, which parameterizes the strength of the measurement given by the coupling between the system and measurement device. And of course, your measurements are not perfect. They may be inefficient. So we parameterize that by a parameter eta. That's just from an experimental point of view to account for non-ideal measurements. So what spikes are is something that I'll be explaining right now. So if you have some kind of a system Hamiltonian, which does not commute with your the measurement operator that governs the dynamics, if you plot in a simulation the time trace of the occupation of one of the levels in the stochastic master equation, you'll essentially see something like this, where you have these oscillations that are distorted by these quantum jumps. Because of these photon detections, what you essentially see is the system just tunnels quickly to the ground state. But if sorry, I'll just play that a little more time. Yeah, you see these distortions by these quantum jumps. But if I increase the measurement strength, basically gamma, to a very large value, and I plot the time trace of the occupation probabilities of one of the levels in that case, what I see is this emergent jump process between the levels 0 and 1, which I call pointer states. And that is decorated by these aborted jumps, what looks like aborted jumps, which we term as spikes. Now, what's interesting is that you can increase the measurement strength to arbitrary levels, and these spikes will persist. And of course, a simulation you can only go to large and finite gammas, but mathematically it's been proven that if you take gamma tends to infinity, the emergent stochastic process of these spikes will persist, they exist. And so essentially our motivation is to explore this phenomena in greater detail. But obviously we're not the first ones to discuss this phenomena. There's been some work in the literature. But why should we care about these spikes? Why would this particular regime even be of interest? Because it seems like a physically inaccessible regime. Well, there have been many studies in literature about the quantum Zeno effect, which basically occurs when you have when you freeze the dynamics of a quantum system by very frequently measuring it. So it is relevant to those studies, and also from a more operational point of view, it is interesting because spikes can affect the time of arrival to a particular state. If you had a pure jump process, the time it takes to reach a particular region in the Bloch sphere or of the qubit would be very different with and without the fluctuations. But what we were more excited about these spikes is that they show interesting counting statistics. And I'll elaborate on that. So there have been observations of the spiking process exclusively in simulations, and these are all the bunch of papers that look into that. But the explicit characterization of spike statistics was done by these very interesting papers by Tello et al. And Bernardin et al., which rigorously established for stochastic master equations with Brownian noise, which is very different from the master equations I just showed you, which had jump terms, that you see the heights of these spikes follow a Poisson process with some kind of model agnostic law. So I'll just explain that in this particular thing. So the question that we are asking is, what are the counting statistics of spikes for jump stochastic master equations? And how you would go about counting them is essentially you have these trajectories. You essentially put a certain box and you count the number of maxima in that come in that particular box. And what you'd see is that as gamma tends to infinity, the distribution of this particular process is a Poissonian with a parameter lambda t, where lambda is proportional to the integral of 1 by x square given by the limits of this box. And this particular law is independent of the underlying model, physical model, which give rise to your stochastic master equation. So if the study has already been done for a class of trajectories with Gaussian noise, why are we looking at jump stochastic master equations? Well, the literature survey I showed you only looked at spikes for simulations, right? So it has not been observed yet experimentally, and that's an open question. So Abhishek and I came across some recent papers which simulated these jump stochastic master equations very efficiently. And we thought, okay, maybe if we can leverage those platforms and try to see whether those can be used to observe spikes experimentally, that this could be a very well-motivated problem, if you just look at spikes for jump stochastic master equations. So I'll just give a quick run through the models that we're looking at. We essentially looked at two-level systems that's coupled to some kind of detector with this Poissonian noise term. And the measurement operator V, which governs the dynamics, causes the state to reset intermittently to a particular point in the Bloch sphere, which is the ground state, essentially, the south pole of the Bloch sphere. And the dynamics is composed of a deterministic part and a part of resetting, where you essentially have these flow-like equations, and they get reset to a particular point in the Bloch sphere. And resetting is interesting because there's been a lot of work regarding how stochastic process resetting have you can basically optimize the various parameters like first passage times and all if you independently tune the resetting rate in a stochastic process. But we were interested in leveraging the resetting property because many distributions can be computed as convolutions of resetting field propagators. So it's essentially resetting enables to analytically handle these jump stochastic master equations and the distribution of these spikes. Okay, so the models we consider independently are like if you can put a driving field on the system, or you can put a thermal bath, or you can put additional measurements. And the result that I just showed you, that all these three models will give you the same kind of statistics for the spikes with some proportionality factors that depend on the particular model, but the power law of signature is agnostic to the particular model. Okay. Oh, I'm almost out of time. So I'll just talk about experimental aspects for a couple of slides. So as I said, the open question that still remains is, are spikes observable experimentally? So of course, the infinite measurement strength limit is inaccessible from an experimental point of view, but the statistics of spikes can be deduced in simulations from these heights of these interrupted jumps. And I'll just explain what that means in a couple of slides. So to experimentally detect spikes, one would have to detect the signatures of spikes without relying on the stochastic master equation. And why would that be so? It's because the difference between a simulation and experiment is actually not that much if you use a stochastic master equation, because in a simulation, what we do is we generate synthetic data, we pass it into a stochastic master equation, and we obtain the state of the system at any particular time t. In experiment, you have real data and you pass that in a stochastic master equation and you get the state of the system at time t. You actually don't have direct access to the state of the system at any given time. So if we take this out of the equation and we just have the real data in an experiment, can we somehow reconstruct the statistics of spikes? So to do that, you would need to leverage quantum state tomography, which is essentially looking at from the real data that you have in your hand, trying to deduce what the state of the system is at any given time, rho t, at any given time t. But the challenges with quantum state tomography is that spikes, which are fluctuations, they are usually smoothened out because the time traces that you obtain are from an ensemble of trajectories, and that's where you use quantum state tomography. So they usually get smoothened out. One way to get around this would be to basically post-select a particular trajectory and essentially accumulate many copies of a particular trajectory and try to get enough statistics to deduce the state, but that's usually prohibitively expensive, and you would need exponentially large number of samples to do this. So so like I mentioned, there was a particular very interesting experiment which basically achieved these highly individual photon detections, basically simulated very efficiently these jump stochastic master equations. So the setup is a three-level system with three levels labeled by ground, dark, and bright. And you have a rabbi drive between these two of these three levels, the bright and ground level and the ground and dark level, such that the drive between the ground and bright level is very much larger than the drive between the ground and dark level. So because of which you have rapid jumps occurring at much smaller time scales between B and G as compared to G and D. So the smart thing that these experimentalists did, that they engineered the coupling between an auxiliary cavity, which they used to measure the occupation of the bright level, such that when the bright level is occupied, this auxiliary cavity is measured by, filled with a lot of photons, otherwise the cavity is empty. So when you look at the experimental output, and this is basically the square root of the photons just plotted as a time trace, you can see when it's close to root 5, that's when you can deduce that, okay, level B is occupied. When it's empty, okay, it's not in B. It could be either in G and D. Okay, so what they can conclude from this measurement apparatus is that when the cavity readout goes from a high photon count to a low photon count, it corresponds to a transition, what we call a click. So I'll just quickly go to the upshot of our proposal, which is, as I mentioned, you cannot rely on any stochastic master equation to deduce the spike. So what we have is, we know that spikes are basically interruptions in these jumps, okay? And what these people have done is, on a sequence of no clicks, so they know clicks are transitions from B to G. In a sequence of no clicks, they mapped out the path of the system, this atom, the sea level atom, through the Hilbert space, and they have actually plotted this particular trajectory. So the knowledge of this particular path combined with the times at which the click occurs will enable you to know at what particular heights this particular jump is getting interrupted, and you can essentially obtain experimentally what the distribution of these heights are. So this is our experimental proposal, and I'll just leave it at the summary slide. So thank you so much.
Take questions. There are.
Alan, can you comment on how noise in these systems will change the statistics of the?
Yeah. So noise actually we noticed does not disturb the 1 by x square scaling of the spikes, because there was a case where we coupled the system to a thermal bath. So it induces thermal noise, right? And we modeled that by adding a Lindblad term to this dynamics. And we saw that the 1 by x square scaling of the statistics remain, but the proportionality factor of the spike statistics can change. So you can increase fluctuations by adding more noise, but the scaling is robust against noise. Yeah.
If there are no more questions, let's thank Alan. And this concludes our first session of the day. And thank you for joining us.